Okay, so we start with sequences, series, convergence tests. The basic concepts, for example, for complex sequences and series and tests for convergence and divergence are very similar to those concepts in real calculus. Thus, if you feel at home with real sequences and series and want to take for granted that the ratio test also holds in complex, skip. So then you can skip the section. But we want to read the basics and the easy mathematics for computer scientists. So that's why sequences, the basic definition are as in calculus. An infinite sequence, or briefly a sequence, is obtained by assigning to each positive integer n a number zn called a term of the sequence and is written as z1, z2, so on. Or we can put these numbers in brackets z1, z2, so on. Or briefly, we can say that sequence is denoted with Zn where n is a positive integer. We may also write Z0, Z1, so on, or Z2, Z3, so on, or start with some other integer if convenient. A real sequence is one whose terms are real. So if each term of the sequence is a real number, we can say the sequence is a real sequence. So convergent sequence, what is the convergent sequence? So a sequence Z1, Z2, so on is one that has a limit C, written limit n approaches to infinite, Zn is equal to C, or simply we can say that Zn approaches to C. By definition of limit, this means that for every epsilon greater than 0, we can find an n such that Zn minus C absolute less than epsilon for all n greater than a natural number n. So for a convergent sequence, there is a limit such that if we increase the term Z1, Z2, Z3, so on, this limit of the sequence will approach a certain number called C. So limit n approaches to infinite, Zn is equal to C, or simply Zn approaches to C. By definition of limit, this means that for every epsilon greater than 0, we can find an n such that Zn minus C absolute less than epsilon for all n greater than a fixed number n. Geometrically, all terms Zn with n greater than n lie in the open disk of radius epsilon and center C. See, for example, this figure 361, and only finitely many terms do not lie in that disk. For a real sequence, one gives an open interval of length 2 epsilon and real midpoint C on the real line as shown in figure 362. So a divergent sequence is one that does not diverge, that does not converge. So here is a geometrical interpretation of the convergent complex sequence. So all the terms of the sequence must lie within this open disk. And for a real sequence, the central point is C, or you can say this the convergent point, that is if limit n approaches to infinite, this sequence will converge to point C. So C plus epsilon is to the right side and C minus epsilon is to the left side, and C is the center of the sequence. So it means this sequence is convergent to the point C. Similarly, this sequence is also convergent to the point C, but this is a real sequence and this numerical figure is a complex sequence. Here is an example. So the sequence iota power n divided by n is equal to iota minus 1 by 2 minus iota by 3, 1 by 4, so on, is convergent with limit 0. The sequence iota power n is equal to iota minus 1 minus iota 1, so on, is divergent, and so is Zn with Zn is equal to 1 plus iota power n. Sequence of the real and the imaginary parts. The sequence Zn with Zn is equal to xn plus iota yn is equal to 1 minus 1 over n square plus iota 2 plus 4 by n is 6 iota 3 by 4 plus 4 iota 8 by 9 plus 10 iota by 3 15 over 16 plus 3 iota. It converges with the limit c is equal to 1 plus 2 iota. Observe that xn has the limit 1 is equal to real part of c and yn has the limit 2 equal to imaginary part of c. This is typical. It illustrates the following theorems by which the convergence of a complex sequence can be referred back to that of the two real sequences of the real parts and the imaginary parts. So sequences of the real and the imaginary part. A sequence of complex numbers Zn is equal to xn plus iota yn, where n is equal to 1, 2, so on, converges to c is equal to a plus iota b if and only if the sequence of the real parts x1, x2, so on converges to A and the sequence of the imaginary parts y1, y2, so on converges to B. So we don't need to have a proof, but we can revise it, that how it works. So convergence Zn approaches to C is equal to A plus iota B implies convergence Xn approaches to A and Yn approaches to B, because if Zn minus C absolute value less than epsilon, then Zn lies within the circle of radius epsilon about C is equal to A plus iota B, so that xn minus A absolute value less than epsilon and absolute value yn minus B less than epsilon. Conversely, if xn approaches to A and yn approaches to B, as n approaches to infinite, then for a given epsilon greater than 0, we can choose n so large that for every n approaches to n, xn minus A absolute value less than epsilon over 2, yn minus B absolute value less than epsilon over 2. Okay, so here we can consider as a disk, open disk, and with the central point C, that is the convergence point. So on x-axis, so the point A and corresponding to A, there is a point B. And with the small increment to point A, we have A plus epsilon, and similarly, and corresponding to this point, we have B plus epsilon, and corresponding to A minus epsilon, we have B minus epsilon. Within this disk, if we have a small interval, then we can define it A plus epsilon by 2, B plus epsilon by 2, A minus epsilon by 2, B minus epsilon by 2. So these two inequalities imply that Zn is equal to xn plus iota yn lies in a sphere with center C and side epsilon. Hence Zn must lie within a circle of radius epsilon with center C. So then the series, given a sequence Zn, Z2, so on Zm, we may form a sequence of the sums, that S1 is equal to Z1, S2 is equal to Z1 plus Z2, S3 equal to Z1 plus Z2 plus Z3 plus so on, and in general Sn is equal to Z1 plus Z2 plus 1 Zn. Here Sn is called the nth partial sum of the infinite series or series. So summation m is equal to 1 to infinite, Zm is equal to Z1 plus Z2 plus so on. The Z1, Z2 are called the terms of the series. Our usual summation letter is n unless we need n for another's purpose, as here, and we then use m as the summation letter. A convergent series is one whose sequence of partial sums converges. A convergent series is one whose sequence of partial sums converges. Say, limit n approaches to infinite, Sn is equal to S. Then we write S is equal to m is equal to 1 to infinite, Zm is equal to Z1 plus Z2 plus so on. And call S the sum or value of the series. A series that is not convergent is called a divergent series. If we omit the terms of Sn from 3, there remains for Rn is equal to Zn plus 1 plus Zn plus 2 plus Zn plus 3 plus 1. This is called the remainder of the series 3 after the term Zn. Clearly, if 3 converges and as the sum S, then S is equal to Sn plus Rn. Thus Rn is equal to S minus Sn. Now Sn approaches to S by the definition of convergence. So hence Rn approaches to 0. In applications, when S is unknown and we compute an approximation Sn of S1, S then Rn absolute value is the error. And Rn approaches to 0 means that we can make Rn absolute as small as we please by choosing n large enough. So this we can revise before going to the next steps. So actually we are dealing with the complex sequence. So the basic definition of the sequence is we can say that an infinite sequence, or briefly a sequence, is obtained by assigning to each positive integer n a number Zn called a term of sequence. So this is the definition of sequence. An infinite sequence, or briefly a sequence, is obtained by assigning to each positive integer n a number Zn called a term of the sequence. It means there should be one correspondence between the positive integers and the terms of the sequence. So if we count that 1, so there should be one term. If we count 2, there should be the second term. And if we count 3, there should be third term. So that is why there is a correspondence between the terms and the positive integers. We can write a sequence as Z1, Z2, so on, or we can write these terms in brackets, that is Z1, Z2, so on, or briefly we can write as Z, Zn, where n, we can say that n is a positive integer. We may also write Z0, Z1, so on, or Z2, Z3, or start with some other integer if convenient. Okay. So then what is a real sequence? A real sequence is one whose terms are real numbers. So a real sequence has the terms which are actually real numbers. And now what is the convergent sequence? Convergent sequence. So a convergent sequence Z1, Z2, so on is one that has a limit C. So convergent sequence must have a limit C, you see. A convergent sequence Z1, Z2, so on is one that has a limit C, which can be written as limit n approaches to infinite, Zn is equal to C, or simply we can write Zn approaches to C. So by definition of limit, This means that for every epsilon greater than 0, we can find an n such that Zn minus c absolute value less than epsilon. Geometrically, all terms Zn with n greater than n, all terms Zn with n greater than n lies in the open disk of radius epsilon and center C. So if we say that what is the geometrical interpretation of a convergent sequence, we can say that geometrically all terms Zn with n greater than n lies in the open disk of radius epsilon and center C. So then we can say that limit n approaches to infinite Zn equal to C. So corresponding to this definition, we can draw an open disk with center C and radius epsilon. So this is a convergent complex sequence, and only finitely many terms don't lie in that disk. So there is a possibility is that there are many terms which don't lie in the disk, but for a particular interval. For a real sequence gives an open interval. So if we want to uh, say the geometrical interpretation of a real sequence, then the figure 362 is representing the geometrical interpretation of real sequence. Next is the divergent. A divergent sequence is one that does not converge. So, or we can say that if a sequence is not convergent, then it may be divergent. Okay. And then is the example of convergent and divergent sequence. The sequence is convergent with limit equal to 0, and the next sequence is divergent, and so is Zn with Zn is equal to 1 plus iota power n. So sequence of real and imaginary parts. The sequence Zn with Zn is equal to, because a, so how we can write this, because a complex number can be written as in the sum of two parts. So xn is actually the real part of the complex number and yn is the imaginary part of the complex number. So this sequence can be written as 1 minus 1 over n square. Okay, and so plus iota 2 plus 4 by n, so is 6i 3 by 4 plus so on. We can write like it converges with the limit c is equal to 1 plus 2 iota. Observe that xn has the limit 1, okay, and yn has the limit 2. So these two parts have a different limits. So it means a sequence can have two sequence as a subsequence in it. For example, so this is the this sequence is the sum of two sequences. One is the real parts, and other is the imaginary part. So next is the sequences of the real and the imaginary parts. So that is a result, that is a theorem. A sequence of complex numbers, okay, a sequence of complex numbers where n is equal to 1, 2, so on, converges to c is equal to a plus iota b, again is a complex number, if and only if the sequence of the real parts converges to a and the sequence of the imaginary part converges to b. Okay. And then what is the series? So given a sequence, we may form a, we may form the sequence of the sums. Okay. So it means we can say that sequence of the sums is called nth partial sum. Okay, let's sequence of the sums. Let's see. Mhm. Sequence of the sum S1 is equal to Z1. So this is the sum of the first term. So S2 is the sum of the first two terms. S3 is the sum of the first three terms, and so on. Sn is the sum of the n terms. So here Sn is called the nth partial sum of the infinite series or series. So that is why we can write it sum m is equal to 1 to infinite, zm is equal to z1 plus z2 plus so on. The z1, z2, so on are called the terms of the series. Z1, Z2, so on are called the terms of the series. Our usual summation letter is n, unless we need n for another purpose as here, and we then use m as the summation letter. A convergent series is one whose sequence of partial sums converges. So a convergent series is one whose sequence of partial sums converges. Say limit n approaches to Sn is equal to S. Then we write limit uh, the m is equal to 1 to infinite Zm is equal to Z1 plus Z2 plus so on, and call S the sum or value of the series. A series that is not convergent is called divergent. So a series which is not convergent is called divergent series. If we omit the terms of Sn from 3, there remains Z1. So if we take thus terms other than first n terms, we can write it Rn Zn plus 1 plus Zn plus 2 plus so on. And this is called the remainder of the series. Okay. So this is actually denoted as the remainder of the series after the term Zn. Clearly, if 3 converges, so this is 3. This is 3. So if 3 converges and has the sum S, then we can write a sum of partial sum of n terms plus remainder. So thus we can write as Rn is equal to S minus Sn. Now Sn approaches to S by the definition of convergence. So hence Rn approaches to 0. In applications when S is unknown and we compute an approximation Sn of S, then absolute value of Rn is the error, and Rn approaches to 0 means that we can make absolute value Rn as small as we please by choosing n large enough.